Time. It's something we all experience yet struggle to define. From the moment we wake up to the time we go to bed, our lives are governed by the ticking of the clock. We measure its passage through seconds, minutes, and years, marking milestones and deadlines, birthdays and anniversaries. But what exactly is it? Is it just a human construct, a way to bring order to the chaos of existence, or is it something more fundamental? In our everyday lives, time seems straightforward. We plan our days, schedule our meetings, and set our alarms, all based on the assumption that time is a constant, unchanging flow. It flows consistently, always moving forward, never stopping, never reversing. We see it in the rising and setting of the sun, the changing of the seasons, the aging of our bodies. However, delve deeper, and time reveals itself as a complex and enigmatic concept, deeply intertwined with the very fabric of the universe. It's not just a backdrop against which events unfold, but an active participant in the cosmic dance. Albert Einstein revolutionized our understanding of time with his theory of relativity. He showed us that time is not a universal constant, but a variable that can stretch and compress. He proposed that time is not absolute, but rather relative, dependent on the observer's frame of reference. This means that two people moving at different speeds or in different gravitational fields can experience time differently. This means that time can pass at different rates for observers in different gravitational fields or moving at different speeds relative to one another. A clock on a speeding spaceship ticks more slowly than one on Earth. This mind-bending concept, known as time dilation, has been experimentally verified and has profound implications for our understanding of the cosmos. It suggests that time travel, at least to the future, is theoretically possible. Time, as we perceive it, is intimately connected to space. Together, they form the fabric of the universe, a four-dimensional continuum known as space-time. Together, they form a four-dimensional continuum called space-time. This concept is central to our understanding of the universe, influencing everything from the motion of planets to the behavior of light. Imagine a vast, flexible sheet. This sheet represents space-time. When you place a heavy object on it, the sheet bends, creating a curve. Objects with mass, like stars and planets, create dents or curves in this fabric, influencing the paths of objects moving nearby. This is why planets orbit stars and why we feel the pull of gravity. This curvature of space-time is what we experience as gravity. It's not a force pulling us down, but the bending of space-time guiding our paths. The nature of time is a fundamental question that has puzzled philosophers and scientists for centuries. From the ancient Greeks who pondered its essence to modern physicists who explore its mysteries, time has always been a subject of fascination. From ancient Greek philosophers to modern-day physicists, the quest to understand time has driven countless inquiries and led to groundbreaking discoveries. Each new insight brings us closer to unraveling the enigma, yet also reveals new layers of complexity. Yet, despite our advancements, time remains one of the most profound mysteries of the universe, a concept that continues to challenge our intuitions and reshape our understanding of reality. It is a universal enigma, a puzzle that may never be fully solved, but one that will always inspire wonder and curiosity. To grasp the essence of time, we must abandon the Newtonian idea of time as an independent entity. Newton viewed time as a constant, unchanging flow separate from the physical universe. This perspective, while intuitive, limits our understanding of the true nature of time. Instead, we must embrace the revolutionary concept of space-time, a unified entity where space and time are intertwined. Einstein's theory of general relativity provides the framework for understanding this mind-boggling concept. His equations revealed that space and time are not separate dimensions, but are interwoven into a single continuum. Imagine a vast, four-dimensional fabric where space and time are interwoven. This fabric can be stretched, compressed, and curved by the presence of mass and energy. This is space-time, the very essence of our universe. It is the stage on which all cosmic events unfold, from the motion of planets to the expansion of the universe itself. Massive objects like stars and black holes create curves in this fabric, much like a bowling ball placed on a trampoline. The greater the mass, the more pronounced the curve. These curves are what we experience as gravity. Objects move along these curves, following the paths dictated by the warping of space-time. This warping of space-time affects not only the trajectory of objects but also the flow of time itself. Time can speed up or slow down depending on the strength of the gravitational field. Time slows down in stronger gravitational fields. This effect, known as time dilation, becomes especially pronounced near extremely massive objects like black holes. This phenomenon known as gravitational time dilation has been experimentally confirmed and has significant implications for our understanding of the cosmos. It affects everything from the synchronization of GPS satellites to the aging process of astronauts. Consider two identical clocks, one placed on the surface of Earth and the other in orbit. The clock on Earth, experiencing a stronger gravitational pull, will tick slightly slower than the clock in orbit. The clock on Earth, experiencing a stronger gravitational pull, will tick slightly slower than the clock in orbit. This difference, though minuscule in our everyday lives, is measurable and has practical applications in technology and science. While this difference is minuscule in our everyday lives, it becomes increasingly significant in extreme gravitational environments, such as near black holes. Here, the warping of space-time is so intense that time can nearly come to a standstill, offering a glimpse into the profound and mysterious nature of our universe. One of the most intriguing aspects of time is its apparent unidirectionality, often referred to as the arrow of time. This concept has fascinated scientists, philosophers, and thinkers for centuries, as it touches upon the very nature of our existence and the universe itself. We experience time as flowing linearly from the past to the future, never the other way around. This linear progression is something we take for granted in our daily lives, from the ticking of a clock to the changing of seasons. But what dictates this directionality? Why do we remember the past, but not the future? These questions lead us to explore the underlying principles that govern the flow of time. The answer, it seems, lies in the concept of entropy. Entropy is a fundamental principle in thermodynamics and statistical mechanics, providing a bridge between the microscopic world of particles and the macroscopic world we observe. Entropy is a measure of disorder or randomness within a system. In simple terms, it quantifies the number of ways a system can be arranged, with higher entropy corresponding to greater disorder. The second law of thermodynamics states that the entropy of a closed system always increases over time. This law is a cornerstone of our understanding of physical processes and has profound implications for the nature of time itself. This means that the universe is constantly moving from a state of order to disorder. Every process, from the rotting of fruit to the spreading of ink in water, contributes to this inexorable increase in entropy. Imagine a pristine sandcastle on a beach. This sandcastle represents a state of low entropy, where grains of sand are meticulously arranged to form a coherent structure. Over time, wind and waves will inevitably erode the castle, scattering the sand and increasing disorder. This natural process illustrates how entropy tends to increase, leading to the eventual disintegration of ordered structures. This natural tendency towards disorder is a fundamental aspect of our universe and is intimately linked to the arrow of time. As structures break down and systems become more disordered, we perceive the passage of time. The arrow of time emerges from this increase in entropy. It is the reason we see processes like decay and aging, and why we cannot reverse these processes to return to a previous state. As the universe evolves, it moves towards a state of higher entropy, and we perceive this directionality as the forward flow of time. This cosmic journey from order to disorder shapes our understanding of time's passage. While the fundamental laws of physics do not distinguish between past and future, the arrow of time provides a macroscopic directionality to the unfolding of events. It is this arrow that gives our lives a sense of progression, from the cradle to the grave and beyond. Einstein's theory of relativity shattered the illusion of time as a universal constant, revealing its flexible and relative nature. Time, it turns out, is not absolute but rather dependent on the observer's frame of reference. This means that time can pass at different rates for observers in different gravitational fields or moving at different speeds relative to one another. This phenomenon, known as time dilation, has been experimentally verified and has profound implications for our understanding of the cosmos. Imagine two identical twins, one remaining on Earth while the other embarks on a high-speed journey through space. Upon the traveling twins' return, they would find that they have aged less than their Earth-bound sibling. This difference in aging, though seemingly bizarre, is a direct consequence of time dilation. Time dilation occurs not only due to relative motion, but also due to differences in gravitational potential. The stronger the gravitational pull, the slower time flows. This means that time passes slightly slower at sea level than on a mountaintop, where the gravitational pull is weaker. We can perceive the passage of time through the changing seasons, the ticking of a clock, or the aging process, but can we directly observe time itself? The answer is no. Time, unlike space, is not something we can see, touch, or smell. It's an abstract concept that we infer from the changes we observe around us. Imagine trying to describe the concept of up to someone who has never experienced gravity. Without a reference point, the concept would be meaningless. Similarly, time, without the context of change, would be imperceptible. We can measure time, quantify its passage, and study its effects, but we cannot directly observe its essence. It's a reminder that our perception of the universe is limited and that there are still many mysteries waiting to be unraveled. Is time a fundamental property of the universe, or does it emerge from deeper quantum processes? Could time itself be part of a higher dimensional reality?